Have you ever stopped and looked around at the world, the trees, the sky, the screen you're staring at right now, and truly wondered where all of this came from? I mean, really came from. What existed before planets, before stars, before even light itself? What was the very first building block of everything we see, touch, and are part of? It's one of those questions that feels almost too big to ask, but once you do, it pulls you into a mystery that's as thrilling as it is profound. We're going to explore that mystery today, diving deep into the origins of the universe and the strange, elusive particles that sparked it all into being. This isn't just a story about science, it's a story about us, our curiosity, our drive to understand where we come from, and our refusal to accept that some questions are too big to answer. For centuries, humans have looked to the skies and told stories about creation, but today we stand at a point in history where we can actually test those stories. We can peer back in time using mathematics and machinery to catch glimpses of the universe in its earliest moments, and what we're finding is stranger and more wonderful than anything we could have made up. In this video, we're going to uncover 30 incredible theories about the universe's first particles. Some are elegant, some sound like science fiction, and some might just change the way you see reality itself. We'll wander through ideas that span from the intensely mathematical to the wildly imaginative, each one a piece of the grand puzzle of existence. So settle in, open your mind, and get ready to explore how it all might have begun, because this journey isn't just about learning what happened at the start of everything. It's about discovering what it means to be part of a story that's still being written. To understand where we might have come from, we have to start with the idea that shaped our modern view of the cosmos more than any other, the Big Bang singularity. Picture the entire universe, every galaxy, every star, every single atom in your body, compressed into a single point of infinite density and unimaginable heat. This wasn't just a small, dense ball. It was a singularity, a state where the laws of physics as we know them break down completely. There was no space because all of space was inside it. There was no time because time itself began here. Then, in an event that defies full comprehension, this singularity began to expand, and it didn't just expand slowly. It exploded into being, inflating faster than the speed of light in a fraction of a second. In the first fleeting moments of this expansion, the universe was a seething, chaotic soup of pure energy. As it rapidly cooled, that energy began to condense, following the blueprint of Einstein's famous equation, E equals mc squared. Energy transformed into the most basic forms of matter. Within the first second, the building blocks of atoms began to appear. Quarks, the fundamental particles that would later clump together to form protons and neutrons, flickered into existence alongside electrons, which would one day orbit atomic nuclei. For several 100,000 years, the universe remained too hot and dense for these particles to settle down and form stable atoms. It was an opaque, glowing fog of plasma, like being inside the sun. The key evidence for this incredible story is all around us, quite literally. The afterglow of that hot, dense beginning still fills the entire sky. We call it the cosmic microwave background radiation. It's the oldest light in the universe, cooled and stretched by billions of years of expansion into a faint microwave signal. When we point our telescopes at it, we're essentially seeing a baby picture of the cosmos, a snapshot from when it was just 380,000 years old. The tiny fluctuations in this glow are the seeds that, drawn together by gravity, would eventually grow into the vast cosmic web of galaxies we see today. This theory provides the essential foundation for everything else we'll explore. It sets the stage, giving us a timeline and a physical process to investigate. Yet, for all its explanatory power, the Big Bang singularity itself remains one of the greatest mysteries. It tells us what happened in those initial moments, but it doesn't tell us why it happened or what triggered it. What came before the singularity? What caused it to erupt? these are the profound questions that the Big Bang Theory leaves open, the very questions that fuel the other incredible theories we are about to uncover. But if the Big Bang gives us the opening chapter, the next page in the story introduces a twist so radical it solved some of the theory's biggest puzzles. This is the theory of cosmic inflation, first proposed by physicist Alan Guth in the 1980s. He suggested that the universe didn't just expand after the singularity, it inflated. For a breathtakingly short sliver of time, a mere fraction of a second, the cosmos underwent a period of exponential, faster-than-light expansion. It wasn't an expansion into space, it was space itself stretching at an unbelievable rate, smoothing out the entire universe in the process. Before inflation, the primordial universe could have been a chaotic, crumpled mess, full of wrinkles and uneven densities. Think of it like blowing up a balloon that's covered in tiny, random creases. As you inflate the balloon to an enormous size, those creases get stretched out until the surface becomes incredibly smooth and flat. That's precisely what inflation did to the fabric of space-time. It took a potentially lumpy and curved infant universe and stretched it into the vast, uniform, and geometrically flat cosmos we observe today. This idea elegantly solves two major problems left by the classic Big Bang model. The first is the horizon problem. When we look at the cosmic microwave background in opposite directions of the sky, those regions are so far apart that light hasn't had enough time since the Big Bang to travel between them. They should be completely disconnected, like two strangers on opposite sides of the planet who have never met. And yet they have the exact same temperature and properties. How can that be? Inflation provides the answer. These distant regions were once much closer together before the violent stretching began. They were in thermal contact, and then inflation instantly pushed them apart, locking in that uniform temperature. The second issue is the flatness problem. Our universe appears to be remarkably flat on the largest scales, meaning the fabric of space-time isn't curved in on itself or bowing outwards. This is an incredibly precise and unlikely balance. For the universe to still be this flat after nearly 14 billion years of expansion, its initial conditions had to be fine-tuned to an astonishing degree. Inflation naturally explains this. No matter how curved or crumpled the universe was at the start, that period of hyper-stretching would have flattened it out, just like how inflating a balloon makes its surface appear flatter and flatter from any point of view. This brief but monumental event of inflation didn't just smooth everything out, it also provided the initial push for all structure to form. The quantum fluctuations that are always popping in and out of existence at the tiniest scales were suddenly stretched to cosmic sizes by the rapid expansion. These tiny ripples in the fabric of space-time became the gravitational seeds for everything that followed. The slightly denser patches began to pull in more matter through gravity, eventually growing into the vast cosmic web of galaxies, clusters, and superclusters we see illuminating the darkness today. So, in a very real sense, the largest structures in our universe owe their existence to the smallest possible quantum vibrations, magnified by inflation. If the universe's initial expansion was the canvas, then the paint that gave it all its texture and structure came from something almost impossibly small: quantum fluctuations. To grasp this idea, we have to venture into the bizarre and counterintuitive world of quantum mechanics, where the very concepts of empty space and nothingness lose all meaning. In our everyday experience, a vacuum is just void, a complete absence of anything. But in the quantum realm, even the most perfect vacuum is a seething, bubbling sea of activity. Particles and their antimatter counterparts are constantly flickering into existence out of pure nothingness, only to annihilate each other and vanish again almost instantly. This isn't just theoretical, we can observe its effects in labs, so true, perfect nothingness might not even exist. This bizarre behavior is governed by a cornerstone of quantum physics, Heisenberg's uncertainty principle. In simple terms, it states that on the smallest scales, there is a fundamental trade-off. We can never precisely know both the energy of a system and the exact time that energy exists. For an incredibly brief moment, energy can seemingly be borrowed from nowhere as long as it's paid back almost immediately. This creates a constant state of turmoil at the quantum level, with virtual particles popping in and out of existence like bubbles forming and bursting in a glass of soda. The universe, it seems, is never truly still. Now, here's where the story gets truly remarkable. Remember that period of hyper-fast cosmic inflation we just discussed? It didn't just stretch the universe, it also stretched these tiny quantum fluctuations. A random, microscopic bubble of slightly higher density that flickered into existence would have been instantly inflated to a macroscopic size. Imagine a single tiny ripple on the surface of a pond. Now imagine the pond itself suddenly expanding to the size of an ocean in a fraction of a second. That tiny, insignificant ripple would suddenly become a vast, rolling wave. Inflation did exactly that to the quantum foam of the early universe. These stretched-out ripples were not in matter itself, but in the very fabric of space-time, tiny variations in the gravitational field. They became the blueprint for all future structure. Areas that were ever so slightly denser had a tiny bit more gravity, which began to pull in more matter from their surroundings. Over hundreds of millions of years, this process snowballed. Those slight overdensities drew in gas and dark matter, forming the first clumps which merged into galaxies, and those galaxies gathered into the immense cosmic web we observe with our telescopes today. Every galaxy, every cluster, every vast empty void between them can trace its origin back to those random quantum tremors. The profound implication here is that the largest structures in our cosmos, the great walls of galaxies and the vast cosmic voids, owe their existence to the smallest, most random events imaginable. It's a breathtaking connection between the microcosm and the macrocosm. This means the distribution of galaxies in the night sky isn't truly random. It's a fossilized imprint of the quantum noise from the universe's first moments, amplified to a cosmic scale. We are, in a very real sense, living in the amplified aftermath of a quantum event. But if those quantum fluctuations provided the blueprint, what provided the building blocks themselves? This leads us to one of the most ambitious and mind-bending ideas in all of physics, string theory. Imagine if every single particle in the universe, the electrons, the quarks, the photons, was not a tiny, zero-dimensional point, but instead an unimaginably small, vibrating loop or strand of energy. A string. What makes one particle different from another, according to this theory, isn't its substance, but rather the unique way its string vibrates. Much like a single violin string can produce different notes depending on how it's played, a single fundamental string can manifest as an electron, a quark, or even a particle of light, all based on its vibrational frequency. This elegant idea offers a stunningly simple potential answer to a deeply complex question. What is the true, fundamental nature of the universe's first particles? In the string theory view, the very first stable entities to emerge from the hot, dense beginning wouldn't have been point-like particles at all, but these vibrating strings. Their specific harmonies would have determined the properties of the earliest matter and the forces that governed it, all arising from a single, unified underlying principle. For this beautiful mathematical symphony to work, however, the strings require a much grander stage than the 3 dimensions of space and one of time that we experience. String theory only holds together in a universe with 10 or even 26 dimensions. So where are these extra dimensions? Theorists propose they are compactified or curled up into sizes so infinitesimally small that they are completely hidden from our perception. Imagine a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you would discover it has a second dimension curled into a tiny circle. The extra dimensions of string theory are thought to be curled up in a similar, though far more complex, way at every single point in space. This framework also introduces a fascinating concept known as brains, short for membranes. These aren't the membranes of biology, but rather dynamical objects that exist in multiple dimensions. Our entire universe could be a three-dimensional brain, floating like a vast, impossibly thin sheet within a higher dimensional space. This idea leads to some truly profound possibilities. What if the Big Bang wasn't the beginning of everything, but was instead the result of a collision between our brain and another one in this higher dimensional bulk? In such a scenario, the immense energy of that collision could have filled our brain with the hot, dense plasma that marked the start of our cosmic timeline, and the vibrations of the strings within that plasma would have given rise to the very first particles. While string theory remains a work in progress without direct experimental confirmation, its power lies in its potential to be a theory of everything. It doesn't just aim to describe particles, it seeks to weave together the two great pillars of 20th century physics: quantum mechanics, which governs the very small, and general relativity, which describes gravity and the very large, into a single, coherent framework. For the first moments of the universe, when everything was both incredibly small and immensely energetic, such a unification is not just helpful, it is essential for a complete understanding. The vibrations of these tiny strings might be the deepest answer we have to the question of what everything is made of. Yet for all its elegant ambition, string theory isn't the only radical framework attempting to explain the deepest nature of reality. An even more mind-bending idea suggests that our perception of a three-dimensional universe might be nothing more than an elaborate illusion, a cosmic mirage. This is the holographic principle, a concept that turns our intuitive understanding of existence inside out. It proposes that all the information needed to describe our three-dimensional world, including every particle, every force, and every event within it, is actually encoded on a distant, two-dimensional surface that surrounds us. In essence, the rich depth and volume we experience might be a projection, like a hologram emanating from a flat, cosmic film. The origins of this startling idea come from an unlikely place: the study of black holes. In the 1970s, physicist Jacob Bekenstein made a profound discovery. He realized that a black hole's entropy, which is a measure of the hidden information or disorder within a system, is not proportional to its volume as you might expect, but to the surface area of its event horizon. This was a huge clue. In everyday systems, entropy increases with volume. More space means more room for disorder. But a black hole, the most chaotic and disordered object imaginable, stores all its information on its boundary. This suggested that the ultimate limit of how much information a region of space can contain isn't based on how big it is on the inside, but on how large its outer surface is. This discovery was solidified by Stephen Hawking's work on black hole radiation, which showed that black holes aren't completely black but slowly evaporate, posing a terrifying paradox. What happens to all the information about the matter and energy that fell in? If it's truly lost, it violates a fundamental law of quantum mechanics. The holographic principle offers an elegant solution. The information isn't lost inside the black hole, it's never actually passed the boundary. It remains encoded on the event horizon, the two-dimensional surface, and is slowly radiated back out as the black hole evaporates. The three-dimensional interior is just a manifestation of that data. Now take this black hole logic and apply it to the entire cosmos. The holographic principle argues that our universe itself might operate under the same rules. The three-dimensional space we inhabit, with its galaxies, stars, and planets, could be a projection from a two-dimensional shell at the very edge of the observable universe. Every particle that we perceive as having volume and position in 3D space is ultimately just a pixel of information on this vast cosmic boundary. Your entire life and everything in it could be the result of data processing happening on a flat surface at the edge of reality. This has a breathtaking implication for the origin of the universe's first particles. In this view, the Big Bang wasn't the creation of a three-dimensional volume, but the initiation of a projection. The first particles didn't emerge within a space. They were the first bits of data that were decoded to create the illusion of space. Their properties mass, charge, spin weren't inherent to them as 3D objects, but were simply the translated information from the 2D source. The quantum fluctuations that seeded the galaxies, then, weren't fluctuations in a 3D field, but were instead fluctuations in the information density on the lower dimensional surface. This radically redefines what we mean by the fabric of reality. There is no fabric, there is only information. The universe is fundamentally a vast array of bits, and the laws of physics are the software code that governs how those bits are processed and projected into the immersive, three-dimensional experience we all share. It suggests that at the most foundational level, the universe is not made of stuff but of data. And the first particles were the first lines of that cosmic code being executed, bringing a virtual reality of unimaginable complexity into being. While string theory proposes tiny vibrating strings in a higher dimensional space, another profound framework tackles the puzzle of quantum gravity from a completely different angle. This is loop quantum gravity, or LQG, and it suggests that the very fabric of spacetime isn't a smooth, continuous sheet as Einstein described, but is instead woven from a network of incredibly tiny, discrete loops. Imagine the universe not as a blank canvas, but as a vast, dynamic tapestry made of an unfathomable number of interwoven threads. Each thread is a loop of gravitational field, and the way they knot and link together defines the structure of space itself. This idea of quantized space leads to a stunning consequence. There is a smallest possible unit of volume, a tiny atom of space. You cannot have half a unit. Space is not infinitely divisible. In a similar way, time is also quantized, ticking forward in the smallest possible increments. This means the frenetic quantum foam of the early universe wasn't just a sea of energy, but a seething, churning network of these spacetime loops, constantly changing their connections in a dynamic dance. This framework offers a truly revolutionary way to think about the Big Bang. In LQG, there was no singularity, no point of infinite density where the laws of physics break down. Instead, the collapse of a previous universe could have reached a point of maximum density, governed by the quantized nature of spacetime, and then bounced. Our entire cosmos, in this view, could be the result of a big bounce. The immense energy and heat of that rebound would have been the catalyst for everything that followed. The first particles wouldn't have emerged from a singular point, but rather crystallized out of this extremely dense, quantized geometry as it expanded. So how would these first particles have formed? In this woven universe of loops, particles themselves are seen as excitations or particular knots in the spacetime fabric. A specific configuration of loops twisting and linking in a certain way would manifest the properties we recognize as an electron's mass or a quark's charge. The particles aren't things in space, they are specific states of space itself. In the frenetic environment immediately after the bounce, these knots would have stabilized into the first stable matter, their properties dictated by the underlying spin network of quantum geometry. This provides a beautifully elegant solution to the problem of the singularity. There's no longer a mysterious, physics-breaking starting point. Instead, we have a transformation, a cosmic rebound where the quantized fabric of spacetime itself reached a maximum compression and then expanded anew. Loop quantum gravity doesn't just aim to describe what happened after the beginning. It provides a plausible, physical picture of what the beginning itself actually was. A turning point in a potentially eternal cycle of universes. But if our universe began with a bounce or as a projection, could it be that our entire cosmic story is just one among countless others? This brings us to one of the most expansive and humbling ideas in all of cosmology, the multiverse hypothesis. The concept suggests that our universe, with its specific set of physical laws and constants, might not be the only one. Instead, it could be a single bubble in a vast, frothing cosmic ocean of universes, each with its own unique properties and perhaps even its own fundamental rules of physics. This idea finds strong support from the theory of cosmic inflation we discussed earlier. Think of that initial hyper-fast expansion not as a one-time event that created our single universe, but as an eternal process that is constantly happening across a much larger metaphysical landscape. In this eternal inflation scenario, the energy that drives inflation doesn't disappear everywhere at once. Instead, in most regions it decays, stopping inflation and allowing a hot, dense universe like ours to form. But in other regions, the inflationary energy persists, causing space to continue expanding at a fantastic rate. Within these ever-inflating seas, new bubbles of stopped inflation are constantly popping into existence, each one a self-contained universe with its own Big Bang. Our entire observable cosmos is just one such bubble in an infinite, ever-growing multiverse. The implications for the universe's first particles are staggering. In each of these bubble universes, the process of symmetry breaking where the fundamental forces froze out from a unified state could have played out differently. The specific vibrations of strings, the knots in the quantum weave of space, or the projection of holographic data might have resulted in completely different sets of elementary particles. In one universe, the electron might be heavier, preventing the formation of stable atoms. In another, the strong nuclear force might be too weak to bind protons and neutrons, so no atomic nuclei ever form. The first particles in each universe would be the unique foundational code for that particular reality, determining whether it would be barren and empty or rich with complexity. This leads us directly to the anthropic principle, a deeply fascinating and sometimes controversial line of reasoning. It simply observes that the physical constants of our universe appear to be finely tuned for the existence of life. If the force of gravity were even slightly stronger, stars would burn out too quickly for life to evolve. If the nuclear forces were any weaker, hydrogen would be the only element, and planets like Earth could never form. The list of these precise, life-permitting values is long and compelling. The multiverse offers a powerful explanation for this apparent fine-tuning. If there are an infinite number of universes with random physical laws, it's no surprise that we find ourselves in one of the rare ones where the constants are just right for us to exist. We are not here because the universe was designed for us. We are here because we are a product of a universe that could support us. So, while we cannot yet travel to these other universes or observe them directly, the multiverse hypothesis provides a compelling, naturalistic framework for explaining the peculiar luck of our own cosmic circumstances. It suggests that the quest to understand our first particles is about more than just our own origin story. It's about uncovering the local bylaws of our particular cosmic neighborhood. And in doing so, we might be glimpsing the breathtaking diversity of all that is, has been, and could ever be. Building on the idea of a universe born from a bounce, there's another theory that takes the concept of a cyclical cosmos and places it within the dizzying framework of higher dimensions. This is the ekpyrotic universe model, a theory that suggests our entire cosmic history began not with a bang, but with a silent, colossal collision between two vast parallel universes. To understand this, we need to venture into the territory of M-theory, the broader framework that unites different versions of string theory. In M-theory, the fundamental objects aren't just strings, but also higher dimensional membranes, or branes for short. These branes could be enormous, existing in a higher dimensional space known as the bulk. Imagine our entire three-dimensional universe is not all there is. Instead, picture it as a gigantic, flat, three-dimensional sheet, a three-brane floating within a fourth spatial dimension. Now imagine another, parallel three-brain floating a short distance away in this bulk. Each of these brains could be a complete universe unto itself, with its own particles and forces, all trapped to the surface of their respective brain-like images projected on a screen. The forces we know and feel, like electromagnetism, are like paint that can't leave the canvas, but gravity, uniquely, is thought to be able to leak out into the bulk, creating a faint connection between these parallel worlds. In the ekpyrotic scenario, these two brains are drawn together over an immensely long period by the gentle force of gravity stretching between them across the bulk. They don't rush toward each other, they approach slowly, almost imperceptibly. As they draw nearer, the energy in the space between them builds. When they finally collide, that pent-up energy is released in an instant, not as an explosion into space, but as an explosion of space itself. The immense kinetic energy of the collision is converted directly into the hot, dense plasma of matter and radiation that we identify as the hot Big Bang. In this view, the Big Bang is the aftermath of a silent, titanic impact in a higher dimensional reality. This model offers a compelling and elegant alternative to a singularity. There is no mysterious point of infinite density where physics breaks down. Instead, there is a well-defined physical event, a collision between two objects. The first particles in our universe would have been born from the incredible heat and energy of that impact, materializing on the surface of our brain as it rippled and vibrated from the force of the collision. Their properties would be dictated by the specific vibrational modes of the strings attached to our brain, excited into existence by the cosmic crash. A particularly fascinating extension of this idea is the cyclic version of the ekpyrotic model. This proposes that the collision isn't a one-time event, but part of an endless cosmic cycle. After the brains collide, they bounce apart, driven by the energy of the impact. The universe we see today, with its galaxies flying apart, is the result of that rebound. But gravity eventually halts the expansion and begins pulling the brains back together across the bulk. Over trillions of years, the brains will approach each other again, leading to another collision and another Big Bang, birthing a new universe from the ashes of the old. In this breathtaking vision, time has no true beginning or end. It's a perpetual cycle of creation and rebirth, with each new universe inheriting a faint imprint from the one before. Visualizing this is key to grasping its profound implications. Think of it like two enormous, perfectly flat sheets of rubber floating parallel to each other in a vast void. They are drawn together, and when they meet, they don't crumple or tear. Instead, they smoothly pass through one another, and the moment of contact sends powerful vibrations racing across their surfaces. Now, imagine that those vibrating sheets are entire universes, and the ripples on their surface are the quantum fluctuations that will eventually give rise to galaxies. This provides a tangible, mechanical cause for the origin of everything, replacing a singular mystery with a potentially testable physical process. It suggests that the deepest question of all, where did we come from, might have an answer that lies not in our past, but just next door, in a parallel dimension we have yet to perceive. But to truly push back to the very edge of time itself, we must venture into a realm so extreme that the very concepts of space and time lose all meaning. This is the Planck epoch, the first and most mysterious chapter in the universe's biography, a period lasting from time 0 to approximately 10 to the power of -43 seconds after the Big Bang. To even begin to comprehend this timescale, consider this. If you were to compare a single second to the entire current age of the universe, roughly 14 billion years, the Planck time would be to that single second what that second is to the age of the universe. It is an almost unimaginably brief sliver of existence. During this epoch, the universe was compressed into a volume so small it is described by the Planck length, about 1.6 times 10 to the power of -35 meters. At this scale, the energy density was so phenomenally high that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were merged into a single, unified superforce. The universe was a seething, chaotic ocean of pure energy where the distinctions we take for granted today simply did not exist. There was no matter, no light, no gravity as we know it. There was only this primordial unity. This is the domain of quantum gravity, the holy grail of modern physics. Our two most successful theories break down completely here. Einstein's general relativity, which beautifully describes gravity and the large-scale structure of spacetime, predicts a singularity of infinite density. Meanwhile, quantum mechanics, which exquisitely governs the behavior of the very small, requires a well-defined, quantized framework. The two are utterly incompatible under these extreme conditions. To understand the Planck epoch, we need a theory that can marry these two giants, a theory that can describe how gravity behaves when it is as weak and probabilistic as the other forces. This is why this era remains the final frontier of cosmological research. We simply lack the mathematical and physical tools to peer into it directly. So how might the first particles have emerged from this chaos? Theorists propose that as the universe expanded and cooled past that critical 10 to the power of negative 43-second mark, it underwent a phase transition. Much like steam condensing into water droplets as it cools, the unified superforce is thought to have frozen and broken apart. Gravity is believed to have been the first force to separate, decoupling from the other three. This moment of symmetry breaking is where the first identifiable structures could have begun to crystallize from the formless energy. The incredibly hot, dense energy of the unified field could have condensed into the earliest primordial particles, perhaps the first stable strings from string theory, or the first knots in the spin network of loop quantum gravity. Their specific properties would have been determined by the exact nature of that phase transition, setting the initial conditions for everything that followed. Studying this epoch is, by its very nature, incredibly difficult. We cannot recreate such energies in any particle accelerator, current or planned. The energy required to probe the Planck scale is over a quadrillion times greater than what the Large Hadron Collider can achieve. Instead, scientists look for indirect evidence. One promising avenue is the search for primordial gravitational waves, the faint ripples in spacetime that would have been generated by the violent fluctuations of the Planck epoch. Detecting these waves would be like hearing the echo of the universe's first cry. Another approach is to study the cosmic microwave background with ever-increasing precision, looking for unique patterns or imprints that could only have been stamped there by physics at the Planck scale. The Planck epoch represents the ultimate challenge and the final secret. It is the moment when the universe was truly unified, a state of pure potential where the laws of physics as we know them were forged. Unlocking its mysteries wouldn't just tell us how particles emerged, it would reveal why they have the properties they do, and perhaps even answer the deepest question of all: why our universe is governed by this particular set of laws that allows for galaxies, planets, and life to exist. While we've explored how spacetime itself might be woven from loops or how our universe could be a holographic projection, another powerful theory aims to solve fundamental puzzles right within the realm of particle physics. This is the concept of supersymmetry, often called SUSY for short. It's an elegant mathematical idea that proposes a deep and beautiful partnership at the heart of reality, suggesting that for every known particle in the universe, there exists a hidden, super-powered twin. According to this theory, the familiar particles that make up our atoms and light the electrons, quarks, and photons are just one half of a much larger cosmic family. For each of these particles, there should be a supersymmetric partner, a so-called sparticle. An electron would be partnered with a selectron, a quark with a squark, and a photon with a photino. This isn't just a whimsical doubling of the cosmic roster. It's a proposal that solves several major problems in one graceful stroke. One of the biggest issues in the standard model of particle physics is the so-called hierarchy problem. which questions why the force of gravity is so unimaginably weaker than the other fundamental forces. The math suggests that the mass of the Higgs boson, the particle that gives others their mass, should be driven to an enormous scale by quantum corrections, effectively making our universe impossible. Supersymmetry elegantly cancels out these problematic corrections. The superpartners of the known particles would provide balancing quantum effects, naturally stabilizing the mass of the Higgs and allowing for the universe we observe to exist. Now let's wind the cosmic clock all the way back to the very first instance. In the extreme heat and density of the early universe, the energy would have been so high that this symmetry would have been perfectly unbroken. Particles and their sparticles would have been indistinguishable, existing in a state of perfect balance and abundance. They would have been created and annihilated in equal measure, a fundamental and symmetric part of the primordial soup. As the universe expanded and cooled past a critical point, this perfect symmetry would have been lost or broken, much like how liquid water freezes into ice. The superpartners, which are predicted to be much heavier than their familiar twins, would have rapidly decayed away or become incredibly difficult to produce as the universe's energy dropped. But their fleeting existence in those first moments would have been crucial, directly influencing the types and abundances of the very first stable particles that went on to form everything we see. This leads us to one of the most compelling implications of supersymmetry, its intimate connection to the mystery of dark matter. The lightest supersymmetric particle, or LSP, is a prime candidate for this invisible substance that makes up most of the matter in the cosmos. In many SUSY models, this particle, often the neutralino, is stable and does not interact with light, making it completely dark. Billions of these particles, relics from the broken symmetry of the early universe, could be drifting through you at this very moment, their collective gravity sculpting the formation of galaxies and holding them together. Supersymmetry thus offers a potential two-for-one solution, fixing problems in the standard model while also providing a natural, compelling candidate for the universe's missing mass. For decades, physicists have been searching for evidence of these superpartners, primarily at the world's most powerful particle accelerator, the Large Hadron Collider. By smashing protons together at velocities approaching the speed of light, they aim to recreate, for a fleeting moment, the energetic conditions where sparticles might briefly flicker into existence. While the LHC's discovery of the Higgs boson was a triumphant confirmation of the standard model, it has so far not found any direct evidence for supersymmetry. This absence has forced theorists to refine their models and consider the possibility that sparticles are heavier than initially hoped, pushing their production energy beyond our current technological reach. Yet, the mathematical beauty and explanatory power of SUSY keep it as a leading and active frontier of physics, a testament to our enduring quest to find a more complete and unified picture of the cosmos's first moments. But in all this exploration of how particles might have formed, from strings to brains to quantum loops, we're left with one of the most profound and puzzling questions of all. Why do these particles have the exact properties that they do? Why is the mass of the electron precisely what it is, or the strength of the nuclear force so perfectly balanced? It turns out that if any of these fundamental constants were even slightly different, the universe as we know it would be impossible. This uncanny fine-tuning leads us directly to a fascinating and often debated idea known as the anthropic principle. The principle comes in two main forms, often called the weak and the strong versions. The weak anthropic principle is the less controversial of the two. It simply observes that we, as conscious observers, can only exist in a universe that has the right conditions to allow for our existence. Therefore, it's no surprise that when we look around, we find ourselves in a universe with constants finely tuned for life. We are, in a sense, selecting ourselves into a specific cosmic neighborhood. Imagine a puddle of water waking up and marveling at how the hole it sits in is perfectly shaped to hold it. The puddle doesn't consider that the hole shaped itself to the puddle. rather the puddle conforms to the whole. In the same way we conform to the universe's rules, the strong anthropic principle takes a much more radical stance. It suggests that the universe must have those life-permitting properties, that the laws of physics and the constants of nature are in some way compelled to allow for the emergence of conscious life. This version often veers into philosophical or even theological territory, implying a purpose or a design behind the cosmos. For many scientists, this is a step too far, as it introduces an element that is, at least for now, beyond the reach of scientific testing. So how does this relate to the universe's first particles? Each of those initial particles came into being with a specific set of properties, mass, charge, spin, that were dictated by the underlying laws of physics. The process of symmetry breaking that gave us the four fundamental forces could have unfolded in a near infinite number of ways, resulting in a random set of constants. The fact that we ended up with the precise set that allows for stable atoms, long-lived stars, complex chemistry, and ultimately us, seems astronomically unlikely. For particles to form atoms, the nuclear forces had to be strong enough to bind protons and neutrons, but not so strong that all hydrogen would have fused in the early universe, leaving no fuel for stars. The electromagnetic force had to be just right to allow for stable electron orbits. Every single step in the chain from the first quark to the first human relies on this incredibly precise balance. This is where the anthropic principle finds its most powerful partner in the multiverse theory. If our universe is just one bubble in a vast multiverse, each with its own random set of physical laws, then the fine-tuning puzzle vanishes. In an infinite ocean of universes, there will be some where the constants are too weak for any structure to form, others where they are too strong and everything collapses immediately. But there will also be a tiny, fortunate fraction where the numbers are just right. We don't live in a specially designed universe, we simply live in one of the few that could ever have produced observers capable of asking the question. The first particles in our universe weren't special or destined. They were just the winning ticket in a cosmic lottery of unimaginable proportions. This perspective doesn't diminish our existence. It grounds it in a vast, awe-inspiring landscape of possibility, where our ability to wonder about our own origins is the ultimate consequence of a random but fortunate roll of the dice. This idea takes us to one of the most radical frontiers of physics, a concept that completely inverts our understanding of reality, the notion that space-time itself is not fundamental. We've grown up thinking of the universe as a stage, a fixed, continuous background of space and time upon which particles move and interact. But what if that stage is an illusion? What if space and time don't exist at the most basic level of reality, but instead emerge from something else entirely, like a three-dimensional image rendered from a deeper, more abstract code? This is the theory of emergent spacetime. It proposes that the seamless, continuous expanse we move through is actually a collective phenomenon, much like the smooth surface of a lake emerges from the chaotic interactions of trillions of individual water molecules. At the fundamental level, reality might be composed of something far more basic, perhaps a network of quantum bits or qubits, simple units of information that obey the rules of quantum mechanics. In this view, the universe isn't made of stuff located in space. It's made of relationships and connections between these fundamental bits. Space itself is what happens when these bits become entangled and interact with one another in a vast cosmic web. Think of it like a digital image on a screen. A high-definition picture looks perfectly smooth and continuous from a distance, but if you zoom in far enough, you see it's actually composed of tiny, discrete pixels. Each pixel carries a specific piece of information, a color value, and its relationship to the pixels around it creates the illusion of a seamless image. The theory of emergent spacetime suggests our universe operates on a similar principle. The smooth, curved geometry of spacetime described by Einstein is not the foundation, it's the final product. The true foundation is a vast array of interconnected information bits, and what we perceive as a location in space is really just a particular pattern of connections between them. So where do particles fit into this pixelated cosmos? If space-time emerges from quantum information, then particles, electrons, quarks, photons must also be emergent phenomena. They wouldn't be tiny marbles sitting in space. They would be specific, stable excitations or patterns of the underlying informational network. A particle's properties, like its mass or electric charge, wouldn't be innate qualities but would be determined by how information vibrates and flows through this network. An electron, for instance, could be a particular self-sustaining resonance in the web, a kind of standing wave of information that maintains its identity as it moves. Its journey across the emergent spacetime would be akin to a glitch moving across a grid of lights, creating the persistent illusion of a single object in motion. This dramatically challenges our traditional, intuitive view of reality. It means that what we consider to be the most fundamental ingredients of the universe, the particles themselves, are actually secondary. They are shadows on the wall of a deeper, more abstract cave. The first particles in the universe, then, weren't the first things to appear in a pre-existing space. They were among the first stable, self-reinforcing patterns to crystallize out of the chaotic, boiling quantum information network as the universe cooled. Their emergence and the emergence of space were two sides of the same coin, a single process of the universe coming into a stable, structured form from a more primal, non-spatial state. The implications of this are staggering. It suggests that the Big Bang might not have been an explosion in space, but the moment when the cosmic hard drive first booted up and began processing information, generating the illusion of space and time as it did. It provides a potential pathway to unify gravity with quantum mechanics, because if gravity is the curvature of spacetime, and spacetime is an emergent property, then gravity itself must be emergent, a thermodynamic force that arises from the statistical behavior of the underlying quantum bits, much like temperature emerges from the motion of molecules. This is a profound shift, suggesting that the force that holds planets in orbit is itself a consequence of information processing on a cosmic scale. It's a theory that doesn't just explain the first particles, it redefines what we mean by reality itself. Another approach to understanding the very fabric of reality takes a completely different path, focusing not on what things are but on how they are connected. This is the theory of causal sets, and it proposes that the most fundamental thing about the universe isn't space or time or even matter, but the simple, binary concept of cause and effect. The entire cosmos, in this view, could be built from a vast collection of discrete events, with the only fundamental relation between them being a single, elegant rule. One event either precedes another or it does not. Imagine the entire history of the universe laid out not as a flowing river of time, but as a colossal, growing network of points. Each point represents a fundamental event, the smallest possible happening. The only thing that defines these points is how they relate to each other. If one event can influence another, a link is drawn between them. This creates a vast cosmic web of causality, a set of elements with a precise ordering that defines which events come before others. This is the causal in causal set theory. The set refers to the mathematical nature of this collection. It is discrete and countable, meaning there is a finite number of these fundamental events within any given region of spacetime. This idea has a profound consequence. It implies that spacetime is not smooth and continuous, but is instead granular and discrete at the smallest scales. There is a smallest possible unit of time and space, a fundamental atom of reality. This neatly avoids the dreaded infinities that plague other theories of quantum gravity, like the singularities at the heart of black holes or the Big Bang. In a causal set, you cannot infinitely divide space or time because you eventually hit a fundamental, indivisible event. The smooth, curved geometry of spacetime that Einstein described so beautifully emerges from the collective relationships of a vast number of these discrete points. Much like the smooth curve of a mountain range emerges from the precise arrangement of countless individual atoms of rock. So where do particles fit into this cosmic web of cause and effect? If the universe is just a set of events, what is an electron or a photon? In the causal set framework, particles are not primary objects. Instead, they are persistent patterns or chains of causality within the set. Think of a wave moving across the ocean. The wave itself isn't a separate object, it's a specific, organized motion of countless water molecules. In the same way, a particle like an electron could be a specific, stable, self-sustaining chain of causal events propagating through the network. Its properties, mass, charge, spin, would not be inherent labels but would be defined by the precise structure of its causal pathway, the unique way it influences and is influenced by the events around it. A photon, which always travels at the speed of light and has no mass, would be a chain with a very specific, maximally connected causal structure. This approach is celebrated for its stunning mathematical elegance and its parsimony. It starts with the simplest possible ingredients, a set of elements and a single ordering relation, and aims to build up all the complexity of the universe from there. It doesn't require the extra dimensions of string theory or the complex loops of LQG. The theory's core principle, known as the Hauptvermutung, or fundamental conjecture, proposes that all the information about the geometry of spacetime is encoded purely in the causal relationships between these events. If you know the complete causal order of the set, you can reconstruct the entire four-dimensional spacetime manifold. Current research in causal set theory is vibrant and focused on overcoming its biggest challenge, demonstrating how a smooth, four-dimensional spacetime like our own can reliably emerge from what is essentially a random, growing network. Scientists run complex computer simulations, generating vast causal sets according to specific rules, and then analyzing them to see if they approximate the properties of a universe like ours. The Holy Grail would be to see a four-dimensional Lorentzian manifold, the mathematical description of our spacetime, naturally appear from the dynamics of the set. While this remains a work in progress, the theory continues to attract attention for its radical simplicity and its power to sidestep some of the most intractable problems in modern physics, offering a uniquely compelling vision of a universe woven together not by substance but by sequence. To venture even deeper into the connection between information and existence, we arrive at one of the most fascinating puzzles in modern physics, the black hole information paradox. This isn't just a problem about the most extreme objects in the universe. It's a crisis that strikes at the very heart of quantum theory and forces us to reconsider how information relates to the particles that carry it. The story begins with Stephen Hawking's stunning realization that black holes aren't completely black. Through a remarkable quantum process, they can actually emit radiation and slowly evaporate away into nothingness. This process, now known as Hawking radiation, arises from the strange behavior of quantum fields just outside the black hole's event horizon. Remember those virtual particles that constantly flicker in and out of existence in empty space? When this happens right at the edge of a black hole, the gravitational pull can tear these particle pairs apart. One particle falls inward, never to be seen again, while its partner escapes into space, carrying away a tiny amount of the black hole's energy. To an outside observer, it looks like the black hole is emitting a faint glow of particles and slowly losing mass over astronomical timescales. The problem is that this radiation is purely thermal. It's random noise like the static from an old television set. It contains no information about what fell into the black hole. This leads to the paradox. According to the fundamental laws of quantum mechanics, information can never be truly destroyed. It can be scrambled and rendered unrecognizable, but it must be preserved in principle. If you were to burn a book, the information in its pages isn't lost. it's just transformed into the precise arrangement of smoke particles and ash. In theory, with a perfect understanding of physics, you could reverse the process and reconstruct the book. But Hawking's calculation suggested that when a black hole evaporates completely, it takes all the information about everything it ever consumed with it, leaving behind only this random thermal radiation. This would be a fundamental violation of quantum law, a loss of information that physics cannot allow. Now, let's connect this cosmic conundrum back to the universe's first particles. If information is truly fundamental, as theories like the holographic principle suggest, then the very first particles that condensed out of the Big Bang weren't just carriers of mass and charge. They were the first physical manifestations of encoded information. Their properties were the data. The paradox of how information is preserved in the most extreme environments, like a black hole, gives us crucial insight into how that data might have been first written into the fabric of reality. It implies there must be a deeper mechanism, a cosmic law we haven't yet discovered, that ensures information is never lost, only transformed. This dilemma has spawned some truly mind-bending proposed solutions. One of the most radical is the black hole firewall hypothesis. It suggests that rather than a smooth, empty space just inside the event horizon, there might actually be a blazing wall of unimaginably high-energy particles, a literal firewall. This violent boundary would immediately destroy anything falling in, but in doing so, it would scramble and encode the information of that object onto the Hawking radiation being emitted outwards. It's a brutal trade-off. Save the information from being lost, but at the cost of completely violating Einstein's principle that an astronaut crossing the event horizon shouldn't notice anything unusual. They would be incinerated instantly. The firewall is not widely accepted, but it highlights the desperate and creative measures physicists are considering to resolve the paradox. Other ideas are even more exotic, suggesting that black holes don't evaporate completely but leave behind a tiny, information-packed remnant, or that the information is stored in a vast cloud of particles surrounding the black hole. The most promising solution seems to lie in subtle effects within the Hawking radiation itself. Later calculations suggest that the radiation, while appearing random, might actually be subtly correlated in a way that encodes the information of the infalling matter. It would be like a book being burned, but the pattern of the flames and the smoke containing a perfect, albeit incredibly complex, description of every word on every page. The profound lesson from this decades-long puzzle is that information appears to be more resilient than matter itself. The fate of information in a black hole serves as a powerful analogy for the origin of particles in the Big Bang. Just as we now believe information must escape a black hole, it must also have been among the first and most fundamental entities to emerge from the singularity or the bounce. The first particles were likely the stable, physical expression of that initial data, their properties locked in by the breaking of symmetries and the cooling of the universe. Understanding how information behaves at the edge of a black hole is perhaps our best guide to understanding how it was first imprinted onto the particles that went on to build everything we see. While the theories we've explored paint a grand picture of cosmic origins, from colliding brains to emergent spacetime, they all share a common, profound question. How did the fundamental particles acquire the specific properties that allowed them to build our universe? This brings us to one of the most crucial discoveries in modern physics, a mechanism that answers perhaps the most basic question of all: what gives things mass? This is the story of the Higgs field and the monumental event known as electroweak symmetry breaking, a process that forever defined the nature of the universe's first stable particles. To understand this, we need to rewind to a time just after the Planck epoch, when the universe was still an unimaginably hot, dense soup. At these incredible energy levels, the forces of nature were unified. Specifically, the electromagnetic force and the weak nuclear force, which are completely distinct in our everyday world. were merged into a single, elegant force known as the electroweak force. In this state, the particles that would later become the familiar electrons and quarks were all massless, zipping around at the speed of light, indistinguishable from the particles that carry force like photons. It was a state of perfect but unstable symmetry. As the universe expanded and cooled, it underwent a dramatic phase transition, much like steam condensing into liquid water or water freezing into ice. This crucial event is called electroweak symmetry breaking. The underlying laws of physics didn't change, but the environment did, causing the single electroweak force to fracture into the two separate forces we observe today, electromagnetism and the weak nuclear force. But for this split to happen, something needed to break the perfect symmetry. That something is what we now call the Higgs field. Imagine the entire universe is filled with an invisible, all-pervading medium, a kind of cosmic molasses. This is the Higgs field. Unlike other fields which are zero in their lowest energy state, the Higgs field has a non-zero value everywhere. Even in the complete vacuum of empty space, the Higgs field is switched on. When the universe cooled past a critical temperature, this field suddenly shifted into its active state, filling all of space. As the first particles traveled through this newly activated field, they interacted with it. Some particles, like photons, passed through completely unaffected, remaining massless and continuing to travel at light speed. Others, like electrons and quarks, interacted strongly with the field. This interaction is what we experience as mass. It wasn't that these particles were suddenly stuffed with substance. Rather, their movement was impeded by the Higgs field, much like a celebrity trying to move freely through a room filled with adoring fans. The resistance they encounter is their mass. The particle associated with this field, the famous Higgs boson discovered at the Large Hadron Collider in 2012, is not the source of mass itself. Instead, it is better understood as a localized ripple or excitation in the Higgs field. Its discovery was monumental because it confirmed the existence of the field itself, providing the final piece of evidence for this mechanism that had been theorized for decades. The Higgs boson is the signature that the Higgs field is real, a fundamental part of the cosmic fabric. This process was absolutely essential for the formation of the first stable matter. Without mass, particles like quarks and electrons would have continued zipping around at the speed of light, never being able to slow down enough to form atoms. There would be no protons, no neutrons, no atomic nuclei. The universe would be a featureless sea of radiation. The Higgs mechanism gave substance to the universe, providing the necessary friction for matter to clump together and begin the long process of building complexity. It took the chaotic, symmetric energy of the early universe and gave it structure and form, defining the specific properties of the very particles that would go on to become the building blocks of everything, from the smallest grain of sand to the largest galaxy. But what if the Big Bang wasn't a true beginning? What if it was merely a transitional phase, a cosmic reboot from a previous state of existence? This brings us to a theory that radically reimagines our cosmic timeline, pre-Big Bang cosmology. The idea that our universe was preceded by another is not new, but modern physics provides compelling frameworks that move it from pure speculation into the realm of testable science. One of the most elegant of these is conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. Penrose's vision is breathtaking in its scope. He proposes that the universe undergoes an endless series of cycles, or eons. Each eon begins with its own version of a Big Bang and expands outward for billions of years until all matter eventually decays and black holes evaporate through Hawking radiation. In the far, far future, the universe would contain nothing but a sea of massless particles like photons, all traveling at the speed of light. In this extremely sparse and diluted state, a fascinating thing happens. The concept of scale becomes meaningless. Because these particles have no mass, there is no way to define a meter or a second. The universe becomes effectively timeless and sizeless. this is where the conformal part of the theory comes into play. Penrose uses a mathematical concept called conformal rescaling, which allows you to stretch or shrink the geometry of spacetime without changing its shape. In this featureless end-state universe, you can mathematically rescale this vast, empty expanse to look exactly like the hot, dense, small beginning of a new Big Bang. The end of one eon becomes, through this mathematical transformation, the beginning of the next. There is no singularity, no point of infinite density, just a smooth transition from the extremely old and large to the extremely young and small, reset by a loss of all scale. Within this cyclical framework, the fate of particles is extraordinary. At the end of an eon, all massive particles have decayed into radiation, but certain types of information might be able to cross the boundary into the next cycle. Penrose suggests that the gravitational influence of immensely massive objects from a previous eon, like supermassive black holes that collided, could leave faint imprints on the new universe. These imprints would manifest as concentric rings of slightly different temperature in the cosmic microwave background radiation, and incredibly, some astronomers believe they have found tentative evidence of just such patterns. These anomalies, these faint circular whispers in the oldest light we can see, could be the gravitational echoes of a cosmos that existed before our own, evidence of colossal events from a time before time. Other pre-Big Bang models offer different narratives. Some string theory interpretations suggest a universe that existed before the Big Bang in a cold, contracted state, perhaps a vast, empty space that underwent a violent phase transition to erupt into the hot expansion we observe. In these models, the first particles of our universe didn't come from nothing. They were triggered into existence by an event, a collision, a fluctuation, a bounce in a pre-existing reality. The particles themselves might have cycled through different phases, their properties reset or remixed during the transition, but the raw potential for their existence was always there. The profound implication of all these ideas is that the question, what was the first particle, might be incomplete. There may have been no first particle, only an endless cycle of transformation and renewal. The building blocks of reality may have been forged and reforged across countless eons, each cycle setting the stage for the next, in an eternal cosmic dance that has no true beginning and no final end. But to truly grasp the nature of those first particles, we must venture to the very edge of where our theories break down, into a realm of pure chaos and potential. This is the domain of quantum gravity, and one of its most evocative ideas is John Wheeler's concept of spacetime foam. Picture the smooth, continuous fabric of spacetime that Einstein described. Now imagine zooming in closer and closer, down to the Planck scale, a distance so small it is to an atom what an atom is to our entire solar system. At this unimaginable scale, the serene cosmic stage becomes a raging, turbulent sea. The precise geometry of spacetime is no longer calm, it is subject to violent quantum fluctuations. Gravity, warping space and time itself, interacts with the uncertainty principle, and the result is a frenzied, frothing foam. Spacetime is no longer smooth. It is a bubbling, probabilistic foam where tiny wormholes might flicker into existence and vanish, and where the very concepts of before and after lose all meaning. In this chaotic foam, the distinction between something and nothing becomes blurred. The tremendous energy of these fluctuations allows for the constant, spontaneous creation of virtual particle pairs, borrowing energy from the vacuum for a fleeting moment before annihilating each other and paying back the debt. This isn't just theoretical. We can measure the effects of this vacuum energy in the lab through phenomena like the Casimir effect, where two metal plates placed incredibly close together in a vacuum feel a slight push from the quantum activity outside them. The foam is this process, but for spacetime itself, it's as if the universe is boiling at its foundation, with bubbles of distorted geometry constantly forming and popping. So how could the first stable particles emerge from such a turbulent beginning? In the extreme conditions of the very early universe, the energy of the space-time foam would have been immense. A particularly violent fluctuation in this quantum froth could have been amplified and frozen by a rapid event like cosmic inflation. Think of it like a bubble in a pot of boiling water that gets trapped and preserved within an ice cube as the water instantly freezes. A microscopic knot in the foam, a specific, stable configuration of warped space-time could have been locked into place as the universe cooled and expanded, its energy crystallizing into what we would recognize as a fundamental particle. In this view, an electron isn't just a point-like object sitting in space. It is a persistent, stable excitation of the space-time foam itself, a tiny whirlpool in the fabric of reality that maintains its structure. This provides a profoundly different perspective on the origin of matter. Particles aren't things that merely exist within space-time. They are themselves manifestations of space-time's most fundamental, grainy nature. The properties of a particle, its mass, its spin, its charge, could be determined by the specific way that tiny region of foam is knotted and curved. The first particles were not created in the universe. They were the universe stabilizing from its own frenetic, foamy chaos as it expanded and cooled, transitioning from a state of pure, unstructured potential into the structured reality we inhabit today. Yet for all the profound insights into particles born from quantum foam and colliding brains, there remains an even deeper and more mysterious component to our universe, one that has quietly shaped its entire destiny from the very first moments. We've been building a story of the cosmos based on the matter we can see, but this luminous matter, the stars, galaxies, and everything they're made of, accounts for less than 5% of the total content of the universe. The overwhelming majority is composed of two enigmatic entities, dark matter and dark energy. Their influence is not just a later addition, it is fundamental, and many theories now suggest they may have been among the very first actors on the cosmic stage, directly influencing the formation of the particles we call ordinary. Let's start with dark matter, the invisible scaffolding of the cosmos. We cannot see it because it does not interact with light or any other form of electromagnetic radiation. We know it exists only through its immense gravitational pull, which bends light around galaxies and holds fast-spinning galaxies together, preventing them from flying apart. The leading hypothesis is that dark matter is made of a new, yet-to-be-discovered class of particles that barely interact with normal matter. These particles are often called WIMP, or weakly interacting massive particles. Because they don't interact through the electromagnetic or strong nuclear forces, they could have been forged in the extreme heat of the early universe in vast quantities, completely oblivious to the frenetic dance of quarks and photons happening all around them. This leads to a fascinating possibility. Dark matter particles may have been among the very first stable particles to emerge from the cooling primordial soup. While normal matter was still a dense, opaque plasma, constantly buffeted by radiation pressure, dark matter would have been free to start clumping together under its own gravity almost immediately. It would have formed vast, invisible gravitational wells, the first structures in the universe long before atoms could even form. These primordial dark matter halos would have served as the gravitational seeds for everything that followed. The ordinary matter, the protons and electrons that would later make up our bodies and our world, simply flowed into the ready-made gravitational basins carved out by dark matter. In this view, the luminous universe we see is just tracing the outline of a shadowy architecture that was built first. Dark energy presents an even deeper puzzle and a more radical potential influence on the first particles. Unlike dark matter, which pulls things together through gravity, dark energy is a repulsive force causing the expansion of the universe to accelerate. We understand it even less, often associating it with the energy of the vacuum of space itself. If this energy has been a constant feature of the cosmos, as some models suggest, then its repulsive force would have been a dominant player even during inflation and the Planck epoch. This constant push against gravity could have directly influenced the process of symmetry breaking, perhaps altering the masses of the very first particles or even determining which particle species survived and which decayed away. The precise value of the dark energy density appears to be another example of incredible fine-tuning. If it were much larger, the universe would have expanded too rapidly for any galaxies or stars to ever form. Its presence, therefore, was not a late-stage addition but a foundational parameter written into the universe's first lines of code, setting the stage for which particles could build a complex cosmos and which could not. Some of the most compelling theories attempting to unify these dark components with the origin of matter involve the concept of the dark sector. This is the idea that dark matter and dark energy are not just single, isolated phenomena, but part of a whole hidden universe of particles and forces that operate parallel to our own. Just as our visible world has protons, neutrons, electrons, and photons governed by forces, the dark sector could have its own rich particle physics, with its own dark protons, dark electrons, and dark photons interacting through dark forces. This entire complex dark world would have co-evolved alongside ours from the very first instance. The first particles of the dark sector would have decoupled from normal matter almost immediately after their creation, going their separate ways and evolving under their own rules, yet forever bound to us through the relentless pull of gravity. The implications of this are staggering. It suggests that the Big Bang did not produce one kind of matter, but two separate worlds simultaneously. We are only seeing half of the picture. The formation of our first particles might have been indirectly shaped by events in this dark sector. For instance, the decay of a heavy, primordial dark matter particle could have released energy that reheated the normal matter, affecting its thermal history and the timing of when protons and neutrons formed. The gravitational influence of early dark matter clumps would have created tiny variations in density that amplified the quantum fluctuations from inflation, directly determining where the first stars would eventually ignite. Our entire visible universe, in all its splendor, may be the afterglow of a deeper, darker reality that began first, making the search for the universe's first particles a hunt that may lead us into the dark. Now, after exploring these grand cosmic frameworks, let's turn our attention to a thought experiment so bizarre it seems like it was pulled from the pages of a science fiction novel. Yet it poses a serious challenge to our understanding of reality itself. This is the Boltzmann brain paradox, a concept that asks a deeply unsettling question. What if the universe's first conscious observer wasn't a complex organism that evolved over billions of years, but a single, disembodied brain that spontaneously formed from a random quantum fluctuation? The paradox gets its name from the 19th century physicist Ludwig Boltzmann, who helped develop our modern understanding of entropy, which is essentially the measure of disorder in a system. The second law of thermodynamics states that the total entropy of the universe always increases. Things move from order to disorder. A cup of hot coffee cools down to room temperature. It doesn't spontaneously heat up. But Boltzmann realized that in a vast, eternal universe, the random jostling of particles will, by sheer statistical inevitability, occasionally lead to a highly ordered state. It's incredibly unlikely, like a tornado blowing through a junkyard and accidentally assembling a perfectly working airplane, but given enough time and enough space, it's not impossible. Now apply that logic to the origin of consciousness. In an infinite or near-infinite universe, the random motion of particles could theoretically arrange themselves into a fully formed, conscious brain, complete with a lifetime of fabricated memories and sensory experiences all in an instant. This Boltzmann brain would flicker into existence, believe itself to be a real person living in a real world, and then just as quickly dissolve back into chaos. The terrifying implication is that, statistically, it's infinitely more likely for a single, isolated brain to randomly form with the false memory of a universe than it is for an entire, ordered cosmos with galaxies, stars, and planets to evolve naturally. So, if that's the case, why are we part of a vast, coherent universe, and not just fleeting, disembodied thoughts in the void? This wild idea has a direct and fascinating connection to the origin of the universe's first particles. Think back to that chaotic, seething quantum foam of the Planck epoch or the inflationary period. It was a realm of extreme energy and maximum randomness where particles and energy fluctuated wildly. In such an environment, the spontaneous, random assembly of a complex structure, while still astronomically improbable, was far more likely than it is in our cold, calm, and spread-out universe today. The first stable particles themselves could be seen as much simpler, more probable examples of this same principle, ordered states briefly emerging from the chaos. The Boltzmann brain paradox isn't presented as a likely theory for our origins. Physicists largely see it as a serious problem that any cosmological model must avoid. It's a reductio ad absurdum argument that shows the absurd consequence of taking certain ideas to their logical extreme. It challenges models that propose an eternal, infinitely large universe because in such a universe, these random fluctuations should be not just possible but common. The fact that we observe a universe that is coherent, ordered, and appears to have a clear history is powerful evidence against such eternal models, or at least forces them to find a way to avoid this bizarre conclusion. Ultimately, the paradox serves as a profound reminder of the incredible, against all odds nature of our existence. It highlights the immense improbability of the order we see around us, an order that began with the formation of the first stable particles and culminated in us, conscious beings able to ponder our own origins. It suggests that the story of our universe isn't just one of particles cooling and clumping together, but a story of information organizing itself against the relentless pull of entropy, creating pockets of order so intricate they can eventually become aware of themselves. What if every particle, every force, every law of physics you've ever known wasn't a fundamental truth of nature, but simply a line of code in an unimaginably advanced simulation? This is the simulation hypothesis, a theory that pushes the boundaries of cosmology from the physical into the realm of the digital, suggesting that our entire reality might be a vast computed construct. In this view, the search for the universe's first particles isn't a quest for physical objects, but a search for the foundational algorithms that the simulation first executed to render our existence. The modern argument for this idea was most famously formalized by philosopher Nick Bostrom. He presents a trilemma, a logical argument with three possible conclusions, one of which he argues must be true. First, almost all civilizations at our level of development go extinct before achieving the technological capability to create realistic simulations. Second, if they do survive, they almost certainly lose interest in creating such simulations. Or third, we are almost certainly living in a simulation right now. The reasoning is that if even one advanced civilization ever runs a significant number of high-fidelity simulations of their ancestors, the number of simulated minds would vastly outnumber the biological ones. Therefore, statistically, any randomly selected conscious being is more likely to be simulated than real. It's a cold, probabilistic argument that forces us to confront the very nature of our own reality. So how does this redefine the first particles? If our universe is a simulation, then the Big Bang wasn't a physical event but the initiation of a program. The first particles wouldn't be vibrating strings or knots in space-time. They would be the first stable data structures rendered by the simulation's engine. Their properties, mass, spin, charge, aren't dictated by a Higgs field, but are instead assigned variables within the code. The fundamental constants of nature, the seemingly arbitrary numbers that are so perfectly fine-tuned for life, wouldn't be laws of physics but rather chosen parameters, perhaps entered by a programmer or generated by a higher-level algorithm. In this digital genesis, the quest to find a theory of everything is the quest to reverse engineer the source code of the simulation itself. This idea finds eerie resonance with some of the deepest puzzles in quantum mechanics. The observed phenomena of wave-function collapse, where a particle exists in a blur of probability until it is measured and forced to choose a state, behaves remarkably like a computer program that only renders the fine details of a scene when a player looks directly at it. This is a common technique in video game designed to conserve processing power. Distant mountains are just low-resolution textures until the player approaches, saving computational resources. The infamous double-slit experiment, where particles seem to know whether they are being observed, could be interpreted as the simulation optimizing its rendering process, only calculating a definite path when the outcome needs to be displayed to a conscious observer within the system. The simulation hypothesis also provides a startlingly elegant framework for the theories we've already explored. The holographic principle, which suggests our 3D universe is a projection from a 2D surface, fits perfectly as a data compression scheme. The quantized nature of space and time in theories like loop quantum gravity could be seen as evidence of a discrete, pixelated reality, the fundamental resolution of the simulation. Even the apparent fine-tuning of the universe for life makes sense. We exist in a simulation that was specifically created with parameters that allow for complex structures like stars, planets, and ultimately, conscious observers to emerge. We are not the unlikely winners of a cosmic lottery. We are the intended inhabitants of a designed reality. Naturally, this is a controversial idea, met with both fascination and skepticism from the scientific community. Critics argue it is an untestable, metaphysical speculation that doesn't qualify as real science. How could we ever prove we are in a simulation? Some, however, have proposed potential tests. One idea is to look for glitches or rounding errors in the fabric of reality, places where the simulation might cut corners. Another is to search for evidence of a fundamental resolution limit to spacetime, a signature that the universe is indeed discrete and not continuous. If we were to ever perform a complex computation that demanded more resources than the entire universe could possibly contain, and yet we succeeded, it might suggest those resources are being provided from outside our perceived reality. Whether you find the simulation hypothesis compelling or deeply unsettling, it represents the ultimate convergence of physics and information theory. It suggests that at its core, reality may not be made of stuff but of bits. The first particles were the first bits, and the laws of physics are the algorithms that process them. This doesn't necessarily make our experiences any less real. The emotions you feel, the stars you see, the love you share, all have meaning within the context of the simulation. It simply means that the ultimate nature of our existence might be far stranger and more wondrous than we ever dreamed, written not in the language of mathematics, but in the silent hum of a cosmic processor. While the Big Bang presents a singular, explosive beginning, another compelling theory offers a radically different vision, one not of a single creation event, but of an endless, cyclical rebirth. This is the ekpyrotic universe model, a concept that suggests our entire cosmic history began not with a bang, but with a silent, colossal collision between two vast parallel worlds. To grasp this, we need to venture into the territory of M-theory, the broader framework that unites different versions of string theory. In this view, the fundamental objects aren't just strings, but also higher dimensional membranes, or branes for short. These branes could be enormous, existing in a higher dimensional space known as the bulk. Imagine our entire three-dimensional universe is not all there is. Instead, picture it as a gigantic, flat, three-dimensional sheet, a three-brane floating within a fourth spatial dimension. Now imagine another, parallel three-brane floating a short distance away in this bulk. Each of these brains could be a complete universe unto itself, with its own particles and forces, all trapped to the surface of their respective brain-like images projected on a screen. The forces we know and feel, like electromagnetism, are like paint that can't leave the canvas, but gravity, uniquely, is thought to be able to leak out into the bulk, creating a faint connection between these parallel worlds. In the ekpyrotic scenario, these two brains are drawn together over an immensely long period by the gentle force of gravity stretching between them across the bulk. They don't rush toward each other, they approach slowly, almost imperceptibly. As they draw nearer, the energy in the space between them builds. When they finally collide, that pent-up energy is released in an instant, not as an explosion into space, but as an explosion of space itself. The immense kinetic energy of the collision is converted directly into the hot, dense plasma of matter and radiation that we identify as the hot Big Bang. In this view, the Big Bang is the aftermath of a silent, titanic impact in a higher dimensional reality. This model offers a compelling and elegant alternative to a singularity. There is no mysterious point of infinite density where physics breaks down. Instead, there is a well-defined physical event, a collision between two objects. The first particles in our universe would have been born from the incredible heat and energy of that impact, materializing on the surface of our brain as it rippled and vibrated from the force of the collision. Their properties would be dictated by the specific vibrational modes of the strings attached to our brain, excited into existence by the cosmic crash. A particularly fascinating extension of this idea is the cyclic version of the ekpyrotic model. This proposes that the collision isn't a one-time event, but part of an endless cosmic cycle. After the brains collide, they bounce apart, driven by the energy of the impact. The universe we see today, with its galaxies flying apart, is the result of that rebound. But gravity eventually halts the expansion and begins pulling the brains back together across the bulk. Over trillions of years, the brains will approach each other again, leading to another collision and another Big Bang, birthing a new universe from the ashes of the old. In this breathtaking vision, time has no true beginning or end. It's a perpetual cycle of creation and rebirth, with each new universe inheriting a faint imprint from the one before. Visualizing this is key to grasping its profound implications. Think of it like two enormous, perfectly flat sheets of rubber floating parallel to each other in a vast void. They are drawn together, and when they meet, they don't crumple or tear. Instead, they smoothly pass through one another, and the moment of contact sends powerful vibrations racing across their surfaces. Now, imagine that those vibrating sheets are entire universes, and the ripples on their surface are the quantum fluctuations that will eventually give rise to galaxies. This provides a tangible, mechanical cause for the origin of everything, replacing a singular mystery with a potentially testable physical process. It suggests that the deepest question of all, where did we come from, might have an answer that lies not in our past, but just next door, in a parallel dimension we have yet to perceive. But if even a cyclical universe of colliding brains still suggests a kind of beginning within an endless cycle, another theory proposes something even more radical, that the universe simply has no beginning at all. This is the no-boundary proposal put forward by physicists Stephen Hawking and James Hartle. It completely reimagines the starting point of everything, suggesting that asking, "What happened before the Big Bang?" is as meaningless as asking, "What is north of the North Pole?" Hawking and Hartle applied the strange rules of quantum mechanics to the entire cosmos. In the quantum world, particles don't follow single, definite paths. Instead, they explore every possible path simultaneously, and we only see the most probable outcome. The no-boundary proposal says the universe itself did the same thing. There isn't one singular history leading back to a Big Bang singularity. Instead, the universe has every possible history, and they all combine to produce the cosmos we see today. The key insight was to treat time as if it behaves like a dimension of space at the very smallest scales. Imagine the timeline of the universe not as a straight line with a definitive starting point, but as a curve that smoothly rounds off like the surface of a sphere. Just as the South Pole is a specific point on the globe but not an edge or a boundary, you can keep traveling south until you start going north again. The beginning of time is a smooth, curved region, not a sharp, jagged singularity. This elegant rounding off of space-time is what no boundary means. The universe would be finite in size and duration, yet completely self-contained, having no boundary, no edge, and no singular point where the laws of physics break down. It doesn't spring from nothingness, it simply is in a state where the concepts of before and after cease to have any meaning. In this model, the early universe wasn't a seething, infinitely dense point. It was a small, smooth, slightly curved region of space-time, more like a tiny, wrinkled pea than a raging inferno. So how do particles emerge from such a placid beginning? In this smooth, finite state, the distinction between time and space is blurred. The universe would have been filled with a unified quantum field. As this tiny, self-contained universe expanded and cooled, this field underwent a process of symmetry breaking. The smooth, unified geometry began to pinch and differentiate, much like a perfectly smooth sheet of ice developing cracks and ridges as it expands and cools. These pinches and excitations in the fabric of space-time themselves became the first particles. Their specific properties, whether they became an electron or a quark, were determined by the specific vibrational modes of this nascent geometry as it transitioned from a timeless, boundary-less state into the expanding universe with a clear arrow of time that we inhabit today. This provides a profoundly different origin story. The first particles weren't born from a violent explosion or a collision. They crystallized gently from the geometry of a finite, self-contained universe as it defined itself. The quantum fluctuations that seeded all future galaxies weren't magnified from a singularity, but were inherent in the gentle, probabilistic wrinkles of this smooth initial state. It's a vision that trades the drama of a cosmic explosion for the quiet, deep elegance of a universe that simply and seamlessly is. Now, to appreciate the truly bizarre nature of neutrinos, we need to talk about one of their most defining features, chirality. This is a property that describes a particle's handedness, or the relationship between its direction of motion and its spin. For a massive particle like an electron, this isn't a fixed property. If you could outrun an electron, you would see its handedness change. But for a massless particle traveling at the absolute speed of light, its chirality is locked in forever. In the earliest, hottest moments of the universe, neutrinos were likely massless, meaning every neutrino was left-handed, spinning like a left-handed screw as it traveled, and every antineutrino was right-handed. This fundamental asymmetry, written into the laws of physics, may have played a crucial role in shaping the early universe, potentially even influencing why there is more matter than antimatter today. But then, a monumental discovery turned this elegant picture on its head. We now know that neutrinos do, in fact, have a tiny, almost imperceptible amount of mass. This revelation came from the ghostly phenomenon of neutrino oscillation, where a neutrino can spontaneously change its identity mid-flight, morphing from an electron neutrino into a muon or tau neutrino as it travels through space. This chameleon-like behavior is only possible if neutrinos have mass, and it means that the neutrinos we detect today are a constantly shifting quantum mixture of different states. This tiny mass, though minuscule, has enormous consequences. It means that in the first second of the universe, when neutrinos decoupled, they were already beginning this strange quantum dance, and their collective gravitational influence spread across the entire cosmos would have helped pull the first structures of dark matter together, setting the stage for galaxy formation. We can actually see the fingerprints of these primordial neutrinos on the cosmos itself. During the first few minutes of the universe, a process known as Big Bang nucleosynthesis forged the first atomic nuclei, hydrogen, helium, and trace amounts of lithium. The rate at which this nuclear cooking occurred was exquisitely sensitive to how many different types of lightweight particles were present, as they affected how quickly the universe expanded and cooled. The number of neutrino flavors we observe today, 3, perfectly matches the observed abundances of these primordial elements. It's a stunning validation. The shadowy relic of the first second of time left its signature in the very elements that would go on to make up the first stars and eventually our bodies. The quest to understand these elusive particles continues at the frontiers of science. Deep underground, in abandoned mines and beneath mountains, colossal detectors like Super Kamiok and in Japan and the Sudbury Neutrino Observatory in Canada lie in wait, shielded from cosmic rays. They are filled with ultra-pure water or other transparent materials, watching for the incredibly rare flash of light created when a neutrino, against all odds, actually bumps into an atom. These experiments have not only confirmed neutrino oscillation, but are now searching for a rare form of nuclear decay that could only happen if the neutrino is its own antiparticle, a discovery that would have profound implications for our understanding of matter's origin. Even more ambitious projects are reaching back further in time. Telescopes like the Ice Cube Neutrino Observatory, a cubic kilometer of ice at the South Pole instrumented with thousands of optical sensors, are hunting for ultra-high energy neutrinos that have been traveling since the most violent events in the early universe. Detecting these cosmic messengers is like receiving a telegram from the universe's most chaotic teenage years, offering a direct view of processes that are completely obscured by the opaque plasma of the infant cosmos. By studying these faint echoes of the first particles, we are not just learning about neutrinos, we are reading a first-hand account from the universe's very first second, written in the most subtle ink imaginable. But what if the very first structures to form in the universe weren't particles at all, but tiny, voracious holes in the fabric of space-time? This brings us to a theory that turns our understanding of cosmic origins inside out, the idea of primordial black holes. Forget the colossal black holes that lurk in galactic centers, formed from the collapse of dead stars. We're talking about something far stranger and more ancient, microscopic black holes that could have been forged in the incredible pressure of the universe's first second, and whose fleeting existence might have literally seeded the cosmos with the matter we see today. The concept was first proposed by Stephen Hawking, building on the discovery that black holes aren't entirely black. According to his groundbreaking work, black holes should slowly radiate energy and lose mass, a process we now call Hawking radiation. This evaporation isn't a gentle process. It accelerates as the black hole gets smaller, culminating in a violent, final burst of particles and energy. For a star-sized black hole, this process takes longer than the current age of the universe, but for a truly tiny, primordial black hole, the entire life cycle could have been over in a fraction of a second. Now imagine not one, but a countless number of these microscopic entities popping into existence amidst the chaos of the early universe, each one a tiny engine converting gravitational energy into a shower of particles. How could such bizarre objects form? They wouldn't require the collapse of a star. Instead, they could have been born directly from the extreme density fluctuations present in the first instance after the Big Bang. If a region of space happened to be even slightly denser than its surroundings, packed with enough energy, its own gravity could cause it to collapse directly into a black hole, no star formation required. This makes primordial black holes a fascinating potential byproduct of the same quantum fluctuations that seeded all cosmic structure, a kind of gravitational extreme sport happening at the smallest scales. The connection to the universe's first particles is where this theory gets truly compelling. As these tiny black holes evaporated via Hawking radiation, they wouldn't just fade away quietly. In their final moments, they would have released a tremendous burst of energy and a wide spectrum of fundamental particles back into the universe. This process could have effectively reprocessed pure energy into matter, acting as a catalyst that helped populate the young cosmos with the quarks, electrons, and other building blocks that would eventually form atoms. In a very real sense, these evanescent black holes could have been the universe's first particle accelerators and factories, their dramatic deaths contributing directly to the matter content we observe today. This idea also opens up a breathtaking possibility for explaining one of cosmology's greatest mysteries, dark matter. What if a fraction of those primordial black holes didn't completely evaporate? What if some were just large enough to survive to the present day? These remaining black holes, drifting unseen throughout the galaxy and between galaxies, would exert a gravitational pull without emitting any light. They would, for all intents and purposes, be a form of dark matter. This would mean the elusive dark matter isn't made of exotic, undiscovered particles like WIMP, but is instead composed of ancient, fossilized black holes from the dawn of time. This idea has seen a major resurgence lately, with astronomers carefully searching for the telltale signatures of these objects, such as the brief flash of light when one magnifies a distant star through gravitational microlensing. Furthermore, the existence and behavior of primordial black holes sit right at the crossroads of our most fundamental physical theories. Their formation probes the limits of quantum gravity, and their evaporation is a direct consequence of combining quantum mechanics with general relativity. Studying them, even theoretically, gives us a unique laboratory for testing ideas about how space-time behaves under the most extreme conditions imaginable. They represent a tangible link between the quantum weirdness of the very small and the cosmic grandeur of the very large, a remnant of a time when the two were inseparable. Whether they ultimately prove to be the source of dark matter or not, these hypothetical relics force us to confront the deepest questions about how our universe was built, one tiny gravitational knot at a time. While we've explored many incredible theories, from colliding brains to cosmic holograms, they all represent pieces of a much larger, more ambitious puzzle. This brings us to the ultimate dream of physics, a goal that has captivated scientists for over a century: the search for a single, all-encompassing framework that can describe every force and every particle under one elegant mathematical roof. This is the quest for a theory of everything. For all its power, our current understanding of the cosmos is built on two separate and stubbornly incompatible pillars. On one hand, we have quantum mechanics, which masterfully describes the bizarre, probabilistic world of the very small, the behavior of atoms and subatomic particles. On the other, we have Einstein's general relativity, which beautifully explains gravity and the large-scale structure of spacetime, from planetary orbits to the expansion of the entire universe. The problem is that these two theories speak different languages and break down in each other's domains. Quantum mechanics becomes fuzzy when applied to the immense gravitational forces at the heart of a black hole, while general relativity produces nonsensical infinities when it tries to describe the subatomic world. A theory of everything aims to be the universal translator, a single set of equations that seamlessly blends these two worlds into one coherent whole. So how would such a theory describe the universe's very first particles? In this grand unified view, the particles wouldn't be seen as separate, fundamental entities. Instead, they would be different vibrational modes or excitations of a single, underlying substance. Think of it like music. You can have a vast array of different notes, chords, and melodies, but they all arise from the same fundamental principle: vibrations on a string or in a column of air. A theory of everything would be the fundamental principle, and the first particles would be the earliest, most basic notes in the cosmic symphony, their unique properties determined by how this universal fabric first began to vibrate as the universe cooled from its initial unified state. The leading candidates for this ultimate theory are the ones we've touched on, each offering a radically different vision of that fundamental fabric. String theory proposes that the deepest level of reality consists of unimaginably tiny, vibrating loops of energy. The specific resonance of each loop determines whether it manifests as an electron, a quark, or a photon. In this view, the first particles were the first stable harmonies to emerge from the cosmic cacophony of the Big Bang. Loop quantum gravity, in contrast, suggests that spacetime itself is woven from a network of discrete, interwoven loops. Here, particles are seen as particular knots or twists in this fabric. The first particles would have been the most stable knots to form as the quantum foam of the early universe began to settle into a recognizable structure. While their approaches differ, both frameworks share the same magnificent goal: to describe the origin and nature of everything from a single primordial starting point. Achieving this unification is not just an academic exercise, it is essential for understanding the universe's very first moments. During the Planck epoch, when all of existence was compressed into a volume smaller than an atom, the energies were so extreme that quantum effects and gravitational forces were inextricably linked. You cannot possibly describe what happened there without a theory that successfully merges quantum mechanics and relativity. A theory of everything is the only key that can unlock the door to that first fraction of a second, allowing us to peer past the singularity and truly understand how something emerged from what might have been nothing, giving us the final, complete answer to the question of what the first building blocks of reality truly were. But if the very fabric of spacetime is a seething quantum foam, what fills the empty spaces between those fleeting loops and knots? This brings us to one of the most profound and embarrassing problems in all of modern physics, a puzzle so immense it's known simply as the vacuum catastrophe. We've been taught that a vacuum is empty space, a true void, but quantum physics tells a completely different story. According to our best theories, what we call empty space is actually a frenetic, bubbling sea of virtual particles constantly flashing in and out of existence. Every single cubic centimeter of the universe, from the depths of intergalactic space to the vacuum inside a light bulb, is theorized to be brimming with this vacuum energy. The problem is that when we try to calculate how much energy this should represent, the number we get is so astronomically large it should have torn the universe apart within the first microsecond of its existence. Let's put this absurd discrepancy into perspective. Based on the principles of quantum field theory, the predicted energy density of the vacuum should be around 120 orders of magnitude larger than what we actually observe. That's a 1 followed by 120 zeros. To say this is a slight miscalculation is like comparing the size of a single proton to the entire observable universe. It is by far the worst prediction in the entire history of science. This staggering gap between theory and observation is the cosmological constant problem, and solving it is one of the holy grails of physics. It forces us to confront the possibility that our understanding of the quantum vacuum, and perhaps reality itself, is fundamentally flawed in some deep and hidden way. This vacuum energy isn't just a theoretical curiosity. It has a direct and powerful connection to the origin of the universe's first particles and the force that shaped the entire cosmos. Many physicists believe that this energy, often called the inflaton field in its specific early universe form, is what drove the period of hyper-fast cosmic inflation. In this scenario, the universe was initially trapped in a high-energy state, a kind of false vacuum. This state possessed a tremendous density of vacuum energy that generated a powerful repulsive gravity, causing spacetime to inflate at an exponential rate. As this field eventually decayed into a lower-energy, true vacuum, it released its stored energy in a colossal burst, flooding the universe with the hot, dense soup of particles and radiation that became the raw material for everything. The first particles, in a very real sense, may have been the ash from the decay of this primordial vacuum energy. This idea also ties directly into the mystery of dark energy, the force causing the expansion of the universe to accelerate today. Einstein originally introduced the cosmological constant into his equations as a form of vacuum energy to keep the universe static. He later called it his greatest blunder, but modern observations have resurrected the concept. The dark energy we observe today behaves exactly like a very small, but non-zero cosmological constant. The dilemma is that we can't explain why its value is so incredibly tiny compared to the theoretical prediction. It's as if some mysterious mechanism almost, but not quite, perfectly cancelled out this enormous vacuum energy, leaving behind only the faintest whisper of its presence to gently push the galaxies apart. Understanding this cancellation is perhaps the key to understanding why our universe is so perfectly poised for the existence of galaxies, stars, and life. Imagine a universe where time is not a fundamental ingredient, but merely an illusion that emerges from something deeper. This is the startling vision proposed by the Wheeler-DeWitt equation, a cornerstone of quantum cosmology that attempts to unite general relativity with quantum mechanics. Formulated by physicists John Wheeler and Bryce DeWitt in the 1960s, this equation does something no other physical law does. It completely lacks a time variable. In its mathematical framework, the entire universe is described in a single, timeless snapshot, a frozen moment that contains all of reality at once. The equation doesn't tell you how the universe evolves through time. It describes a universe where time itself has no independent meaning. To grasp this, think of a movie. Normally, physics gives us the individual frames and the rules for how one frame leads to the next. The Wheeler-DeWitt equation gives us the entire movie printed on a single, vast sheet of paper. All events, the Big Bang, the formation of stars, your birth, the distant heat death of the cosmos, exist simultaneously in this grand, static picture. This perspective, known as the problem of time in quantum gravity, forces us to ask a profound question. If the most fundamental description of reality is timeless, then what is the nature of the change and flow we experience every single moment of our lives? This leads to a radical rethinking of what particles truly are. In this timeless universe, particles like electrons and quarks might not be tiny objects moving through a pre-existing spacetime. Instead, they could be understood as stable, emergent solutions to the Wheeler-DeWitt equation. They are not things in the universe, they are specific, self-consistent patterns of the universe, much like a standing wave is a specific pattern of motion in a body of water. Their apparent movement and interaction through time would be a consequence of the correlations between these complex patterns within the larger, timeless whole. Your perception of an electron moving from point A to point B is just your brain's way of decoding a small part of this immense, interconnected and static tapestry. The implications for the universe's first particles are staggering. In this view, there was no first moment in time for them to appear. The particles that built the cosmos have always existed, in a sense, as fixed features of this timeless equation. The Big Bang wasn't an event that happened in time. It is simply a particular region or boundary within this eternal structure. This doesn't make the particles any less real, but it profoundly changes their origin story. They are not created, they are inherent mathematical truths of a universe that simply is, challenging us to find a new language to describe a reality where time is not the stage but part of the performance. Now we arrive at a theory that stands as one of the most mathematically profound and philosophically staggering ideas in all of modern physics, the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. Born from the study of string theory and black holes in the late 1990s, this concept proposes a concrete, calculable duality that makes the holographic principle we discussed earlier suddenly feel less like a metaphor and more like a precise operational manual for reality. At its heart, AD-S/CFT posits that a gravitational theory playing out in a certain kind of multi-dimensional universe is completely equivalent to a quantum field theory living on its lower dimensional boundary. It's a discovery that suggests the three-dimensional world we experience might be a projection, a shadow cast by a dizzying quantum dance happening on a distant two-dimensional surface. To grasp this, let's break down the name. Anti-de Sitter refers to a specific hypothetical shape of the universe, one that is negatively curved like the interior of a saddle, and which has a very clear, defined boundary at spatial infinity. This is the bulk space where gravity operates. Conformal field theory describes a very special type of quantum theory that lives on the boundary of this bulk space. Conformal means the theory is scale invariant. It looks the same no matter how much you zoom in or out, which is a property often associated with systems that have no inherent length scale, much like the universe at its very beginning. The correspondence is the breathtaking claim that these two utterly different descriptions, a gravitational universe in, say, 5 dimensions, and a quantum universe on its 4-dimensional boundary, are two different languages describing the exact same physics. They are mathematically equivalent, a complex calculation involving warping space-time and falling objects in the bulk can be perfectly translated into a calculation involving quantum particles and forces on the boundary, and vice versa. This idea finds its most powerful application in solving the black hole information paradox. Imagine a book falls into a black hole. From the perspective of the bulk, the book is lost behind the event horizon, and its information seems doomed to vanish when the black hole eventually evaporates. But from the boundary perspective, the story is completely different. The information contained in that book never actually falls into the black hole. Instead, it is perfectly encoded and scrambled across the quantum degrees of freedom on the event horizon itself, the two-dimensional surface. The Hawking radiation that slowly leaks out isn't random thermal noise. It's the careful quantum mechanical decoding of that information back into the universe. AdS/CFT provides the mathematical dictionary for this translation, strongly suggesting that information is never truly lost. It's just transferred from a three-dimensional format to a two-dimensional one. So what does this extraordinary duality imply for the origin of the universe's first particles? In this framework, the Big Bang might be understood not as the creation of a three-dimensional volume, but as the initiation of a projection. The incredible heat and energy of the primordial fireball wouldn't be the cause of the universe's birth, but rather the result, the three-dimensional manifestation of a specific quantum state on the boundary achieving a critical level of complexity and energy density. The first particles, the quarks, electrons, and photons, wouldn't be the fundamental starting points. They would be the holographic projections of specific patterns of quantum information being processed on the lower dimensional boundary. Their properties, mass, charge, spin, wouldn't be inherent properties of little balls of matter, but would instead be emergent characteristics derived from how that underlying quantum information is entangled and organized. This turns our entire conception of reality inside out. We are used to thinking that the deepest, most fundamental description of an electron is as a point-like particle or a vibrating string. AdS/CFT suggests something even stranger, that the most fundamental description is a specific, intricate pattern of quantum data on a distant surface. The electron itself, with its volume and position, is a three-dimensional interpretation of that data. It's not that the data creates the particle, the data is the particle, and what we perceive is a rendered image. The entire cosmic history of particles forming atoms, stars, and galaxies would then be the unfolding narrative of this boundary quantum system, evolving and projecting its complexity into the immersive holographic show we call the universe. In this view, searching for the first particle is like searching for the first pixel in a movie. It misunderstands the medium. The particles are the output, not the source code. But if we step back from the hologram and the timeless equation, we encounter a force so fundamental to our experience of reality that we often take it completely for granted: the relentless and irreversible flow of time itself. This brings us to a theory that roots the very existence of our universe not in a specific particle or field, but in a fundamental cosmic gradient, the inevitable and universal increase of disorder, governed by the second law of thermodynamics. This law states that the total entropy or disorder of a closed system always increases over time. It's why a hot cup of coffee cools to room temperature, why a sandcastle crumbles in the waves, and why you can easily scramble an egg but can't unscramble it. The universe, on the whole, is moving from a state of order to a state of disorder. To understand how this shapes the story of the first particles, we need to rewind that tape all the way back to the very beginning. The current scientific consensus, supported by observations of the cosmic microwave background, suggests that the early universe was in a state of incredibly low entropy. It was exquisitely ordered, hot and dense, but remarkably smooth and uniform. This is a deeply puzzling starting point. Out of all the possible initial states the universe could have had, why did it begin in such a specific, highly ordered configuration? This mystery is known as the past hypothesis. This incredibly low entropy beginning is the ultimate wound-up spring. It's what gives the universe somewhere to go and provides the arrow of time with its definitive direction. Without this initial order, time would have no consistent flow, and the complex structures we see today could never have formed. Now, imagine the early universe as a perfectly mixed cup of coffee and cream. In our experience, we start with separated coffee and cream, and when we mix them, they become disordered. That's entropy increasing. But the early universe was the opposite. It began as that perfectly mixed, homogeneous state. The mixing that followed was actually the process of the universe developing structure and complexity. As the universe expanded and cooled from that smooth beginning, gravity began to amplify tiny quantum fluctuations. Slightly denser regions pulled in more matter, forming galaxies and stars. This seems like it's creating order from disorder, but on the grand cosmic scale, it's actually a massive increase in entropy. A universe with all matter and energy evenly spread out is a high-entropy, lifeless state of thermal equilibrium, often called the heat death. A universe with clumps of matter, hot stars, and cold, empty space has a much higher total entropy. The formation of every star, every planet, and every person is a step along the road to this ultimate disorder. So how does this entropic journey influence the formation of the very first particles? The transition from the unified forces of the Planck epoch to the distinct particles we know was fundamentally a process of symmetry breaking. Think of it like a perfectly symmetrical, pristine ice crystal melting into a puddle of water. The ice crystal is highly ordered and has low entropy. The puddle is more disordered and has higher entropy. In the same way, the early universe's perfect symmetry represented a state of lower entropy. As it cooled, that symmetry broke, giving rise to the different forces and the diverse families of particles. This breaking of symmetry was a massive increase in entropy. The first particles weren't just created, they were the direct result of the universe navigating its path toward higher disorder. Their specific identities and properties were frozen into place by this cooling, a direct consequence of the cosmic arrow of time pointing firmly toward a more probable, disordered future. This perspective offers a breathtakingly different way to view our cosmic history. The entire narrative, from the first quark to the last dying star, is not a story of creation fighting against decay, but a story of decay itself. The increasing entropy is the engine of complexity. It provided the necessary gradient for particles to acquire mass via the Higgs field, for protons and neutrons to form, and for gravity to sculpt the cosmos. The arrow of time, born from that mysterious low-entropy beginning, is the invisible hand that guided the condensation of energy into the first stable matter, setting the stage for everything that was to follow. In this light, every particle in your body is not just a relic of the Big Bang, but a testament to the universe's relentless, beautiful march toward disorder. And so we arrive at our final theory, a concept that stands apart from all the others by placing consciousness itself at the very center of the cosmic drama. This is the participatory anthropic principle, a profound and deeply controversial idea championed by the legendary physicist John Archibald Wheeler. After a career spent helping to lay the foundations for modern physics, from nuclear fission to black holes, Wheeler began to ponder an even deeper question: what is the ultimate role of the observer in shaping reality? His startling conclusion was that the universe could not exist in a definite state without conscious observation. In a very real sense, we are not just living in the universe only comes into being because we are here to observe it. To grasp this, we need to revisit one of the most bizarre experiments in quantum mechanics, the double-slit experiment. When you fire particles like electrons at a barrier with two slits, they don't behave like tiny bullets. If you don't measure which slit they pass through, they act like waves, creating an interference pattern on the detector screen behind it. They seem to pass through both slits simultaneously. However, the moment you place a measuring device at the slits to determine which path each electron takes, this wave-like behavior vanishes. The electrons suddenly behave like well-behaved particles, and the interference pattern disappears. It's as if the particle knows it is being watched and changes its behavior accordingly. This is the famous quantum measurement problem, and Wheeler expanded this idea to a cosmic scale with his delayed choice thought experiment. He proposed that a measurement made today could retroactively determine the path a particle took billions of years ago, even before life on Earth began. The act of observation now could be influencing events that happened in the distant past. Wheeler took this a step further, coining the phrase "it from bit." He suggested that the fundamental currency of the universe isn't matter or energy, but information. Every particle, every field, every force is ultimately manifested by yes or no questions posed by observations, the bits of information. The tangible, physical universe arises from the bit, the act of acquiring information. In this view, the universe is a self-excited circuit. It bootstrapped itself into existence, but only achieved a concrete, definite reality when it eventually evolved observers who could look back and measure it. The first particles didn't just exist in a void, they existed in a state of quantum potential, a fog of possibilities. Their transition from fuzzy probability waves into solid, measurable entities may have required a participant, a conscious observer, to complete the process. This leads to the most breathtaking implication for the universe's origin. The Big Bang wasn't a one-time event that set everything in motion. Instead, it was the beginning of a participatory loop. The universe expanded and cooled, allowing for the formation of galaxies, stars, and planets. On at least one of those planets, life evolved, and eventually conscious beings emerged. Those beings, through the act of observation and measurement, then retroactively gave definite form to the quantum possibilities of the past, solidifying the history that led to their own existence. We are not just the products of the universe, we are its necessary collaborators, finishing the job of creation by forcing its potential into actuality. Of course, this idea is met with intense skepticism. Critics argue it veers into metaphysics and mysticism, placing an untenable importance on human consciousness. They ask what exactly qualifies as an observer. Is it a human, a cat, a photon-detecting machine? The theory struggles with these definitions. Furthermore, it seems to put the cart before the horse, suggesting that an effect in the future can cause something in the past, which clashes with our fundamental intuition about cause and effect. Yet, Wheeler's genius was to push us to confront the strange implications of our own best theories. The participatory anthropic principle may not be a complete or proven theory, but it serves as a powerful reminder that in the quest to understand the cosmos, we cannot fully separate the observer from the observed. We are not passive inhabitants of a predetermined reality. We may be active players in a grand cosmic story that is still being written with our own consciousness as the pen. From the explosive birth of the Big Bang singularity to the silent cosmic collision of the ekpyrotic model, from the elegant vibrations of string theory to the pixelated reality of emergent spacetime, we have journeyed through 30 incredible windows into the origin of everything. Each theory, whether grounded in robust mathematics or soaring on the wings of imagination, offers a unique and compelling perspective on that ultimate mystery. What were the very first particles, and how did they spark our entire cosmic story into being? We've seen how the quantum foam of the Planck epoch might have crystallized into the first knots of matter, how the inflationary stretching of space amplified microscopic fluctuations into galactic seeds, and how the Higgs field gave substance to a formless energy. We've considered the possibility that our universe is a holographic projection, a digital simulation, or one bubble in an infinite multiverse. We've explored cyclical universes that bounce and brains that collide, and we've even dared to ask if our own consciousness might play a role in finishing the act of creation itself. What unites these wildly different ideas is not a single answer, but a shared, profoundly human drive to understand our place in the cosmos. This is not a story with an ending, it is an ongoing, exhilarating quest. Every new observation from our telescopes, every new collision in our particle accelerators, and every new equation scrawled on a theorist's chalkboard brings us closer to discerning which of these breathtaking visions might be true. The very fact that we can formulate and debate such profound concepts is a testament to our curiosity and our refusal to accept that any question is too big to ask. This journey doesn't end here. It continues in the labs and observatories around the world, and it continues with you. Now we want to hear from you. Which of these 30 theories resonates the most? Does the timeless elegance of loop quantum gravity capture your imagination? Or are you captivated by the holographic principle's radical reimagining of reality? Share your favorite theory in the comments below. We love reading your thoughts and diving into these discussions with our incredible community. If these cosmic mysteries ignite your curiosity, make sure to subscribe and hit the bell so you don't miss our next exploration into the deepest questions of science and existence. The universe is full of secrets waiting to be uncovered, and together we can continue to push the boundaries of what we know. Thank you for joining us on this incredible journey to the very beginning